So we have a physics PhD qualifying exam practice problem number 21. So let's begin. A Brownian particle of mass m satisfies the Langevin equation, and I apologize if I'm not pronouncing that properly. I'm not good at languages. Langevin equation, m dv dt equals negative gamma v plus eta of t, where the stochastic force satisfies the expectation value eta of t equals 0 and expectation value eta of t prime equals a delta, and I apologize for that delta, t minus t prime. So for part A, solve the Langevin equation and determine the velocity or autocorrelation function of that expectation value v of t, v of 0. So this is a fluctuation theory and Brownian motion problem. So part A, mv dot equals negative gamma v plus eta of t, where the expectation value of eta of t equals 0. That expectation value eta of t prime, that equals a delta t minus t prime. We're going to let tau equal m over gamma, so the equation becomes v dot plus 1 over tau v equals eta of t over m. So velocity or autocorrelation, what we're going to do is multiply the integrating factor here for this differential equation by e to the t over tau. So we take dt of e to the negative t over tau v of t, and set that equal to e to the t over tau over m eta of t. So integrating here, v of t equals v of 0 e to the negative t over tau plus 1 over m integral from 0 to t e to the negative quantity t minus s divided by tau eta of s ds. So now multiplying by v of 0, averaging the expectation value v of t, v of 0, that equals v of 0 squared. Expectation value of that, e to the negative t over tau, plus 1 over m times the integral from 0 to t, e to the negative quantity t minus s over tau, expectation value of eta of s, v of 0 ds. Okay, so that's the first part of part A, and just moving along here. Sorry about that. So now the second part here of part A. Assume the noise is uncorrelated with the initial equilibrium velocity. That expectation value eta of s, v of 0, that's equal to 0. So the expectation of value of v of t, v of 0, that equals the expectation value of v of 0 squared times that e to the negative t over tau. And at the equilibrium, 1 over 2m times the expectation value v squared, that equals 1/2 k sub bt. So expectation value v squared, that equals k sub bt over m, and the expectation value of v of t, v of 0, that equals expectation value of v of 0 squared times e to the negative t over tau. And at the equilibrium, 1/2 m times that expectation value of v squared, that equals 1/2 k sub bt. Therefore, expectation value of v squared, that equals k sub bt over m. So we could say that the expectation value of v of t, v of 0, that's equal to k sub bt over m times e to the negative gamma t divided by m. And the expectation value here, v of t prime, that equals k sub bt over m, e to the negative gamma to e to the negative gamma times the absolute value of t minus t prime, and that quantity divided by m. That, and then right here in the, this is the numerator after raising that, this is e to the negative gamma, absolute value t minus t prime in the numerator divided by that m. Okay, so that's part A. Part B, For part B, they want us to derive the mean squared displacement, the x squared of t, for arbitrary time. So that's from here, mean squared displacement, we're going to let x of t minus x of 0 equal the integral from 0 to t v of s ds, and the expectation value here of this quantity x of t minus x of 0 squared equals this integral here, 0 to t ds times the integral 0 to t ds prime of that expectation value v of s prime. We're going to use this expectation value v of s prime, set it equal to k sub bt over m, e to the negative absolute value of s minus s prime over tau. So then expectation value of the quantity x of t minus x of 0 squared, that equals k sub bt over m times the integral from 0 to t ds times 0 to t ds prime e to the negative absolute value of s minus s prime, that divided by tau. So from there, if we utilize symmetry, 0 to t ds, 0 to t ds prime, e to the negative absolute value of s minus s prime over tau, that equals 2 times 0 to t ds, 0 to s ds prime, e to the negative quantity here, s minus s prime over tau. So we're going to let u equal s minus s prime. So from 0 to s ds prime e to the negative quantity s minus s prime over tau, that equals the integral integrating from 0 to s of e to the negative u over tau du, and then carrying out the computation, that equals tau times the quantity 1 minus e to the negative s over tau. Now, building on that for the rest of letter B. Whoops, sorry about that. So expectation value of x of t minus x of 0 squared, that equals 2 k sub bt over m times the integral from 0 to t tau times the quantity 1 minus e to the negative s over tau ds. That equals that equals 2 k sub bt over m times this whole quantity, bracket tau t minus tau squared times the quantity 1 minus e to the negative t over tau, close bracket. And since tau equals m over gamma, we could say the expectation value of the quantity x of t minus x of 0 squared, that equals 2 k sub bt over gamma times the quantity t minus m over gamma times this 1 minus e to the negative gamma t over m, and close bracket. Okay, and that's for letter B. For letter C, they want us to show explicitly that in the long time limit, the system approaches diffusive behavior. So for part C, long time diffusive limit. So for t is much greater than tau equals m over gamma, we have e to the negative t over tau, that's approaching 0. And this expectation value of x of t minus x of 0 squared, that's approximately equal to 2 k sub bt over gamma t. So the diffusion law in one dimension is expectation value of x of t minus x of 0 squared equals 2 dt. So d is going to equal k sub bt over gamma. So that's letter C. For letter D, they want us to derive the Einstein relation connecting the diffusion constant and the friction coefficient. So Einstein relation for this. So what we can say here, Einstein relation, the mobility mu is defined by the response to a constant force F. So this gamma V drift equals F, that V sub drift equals F over gamma. So mu equals V sub drift over F equals 1 over gamma, D equals K sub BT over gamma. So the Einstein relation is D equals mu K sub BT. And for letter E, they want us to determine the constant A using the fluctuation dissipation theorem. Okay, so part E, determine A, we're going to use stationary and equilibrium variance. So from the stochastic equation, V of t equals 1 over m times the integral from here, negative infinity to t, e to the negative quantity t minus s over tau, eta of s ds, then the expectation value, v squared of t, that equals 1 over m squared, integral from a negative infinity to t ds, negative integral here, negative infinity to t ds prime e to the negative quantity t minus s over tau times e to the negative quantity t minus s prime over tau times that expectation value of eta of s prime right here. So we're going to use expectation value of eta of s prime, that equals a delta, my apologies for that delta, drawn that way. So a delta times the quantity s minus s prime, and expectation value v squared, so I'm sorry, a delta s minus s prime, and the expectation value of v squared, that equals a over m squared, and then the integral of negative infinity to t, e to the negative 2 of t minus s over tau ds. So from here we're going to let u equals t minus s. So this integral here from negative infinity to t of that not negative, that's e to the negative 2 of times, let me start from here, this integral from negative infinity to t, and then we're integrating here using e to the negative 2 times t minus s over tau ds. And that equals integral from 0 to infinity e to the negative 2 u over tau du equals tau over 2 when we perform the computation. So our expectation value of v squared, that equals a over m squared times tau over 2. And that would equal a over m squared times m over 2 gamma. So we get a over 2 m gamma. Now from there, at the equilibrium, sorry about that. So at the equilibrium, expectation value of v squared equals k sub bt over m. So a over 2m gamma, that equals k sub bt over m. So a equals 2 gamma k sub bt. And the noise correlation is going to be the expectation value of eta of t prime equals 2 gamma k sub bt delta t minus t prime. Okay, so thank you very much for that, and have a great day.